Я имею в виду, что он показывает 21 день с учетом того, что у меня за мой рабочий год, который до...
Так, добрый день тем, кто пришел. Давайте начинать. Скажите кто-нибудь что-нибудь, чтобы я услышал вас.
Добрый день.
Ага, спасибо, слышу все. Значит, окей. We continue starting list decoding. Recall the main definition. So we say that the code C is EL list decodable if every Hamming ball of radius E has at most L code words. And we have established necessary and sufficient conditions for existence of a list decodable code with given parameters. And now we will find out what happens for particular calls for which parameters they are least decodable. And the best code, I mean the best results can be obtained from Adamar code. So we will start least decoding Adamar code. First of all, let's recall, let me remind you what Adamar code is. So Adamar code has parameter 2 to the m, where m is an arbitrary integer, m plus 1, and the distance is half of the block length. The alphabet is binary. And messages are identified with affine functions of m variables. Affine functions. And the code of that function is the table of its values, which obviously has length 2 to the m because there are 2 to the m possible assignments of values. Tables of affine functions. So the maximum number of errors the code allows to correct is half of the distance. And for list decoding, we can actually, so the necessary and sufficient conditions say that with a small list, we can decode up to approximately so let's recall the necessary and sufficient condition from the last lecture. More or less, they are the following. So the volume of the Hamming ball of radius n times 2 to the k is at most 2 to the n, if and only if. This is an approximate statement. So the code is there is n k. Actually, this was for, we proved it for any alphabet, but now we are interested only in the binary alphabet. So let's take 2SQ. EL is the decodable code. Code exists. More specifically, for the sufficient necessary condition, we need to multiply this by L. For the sufficient condition, we don't multiply the right-hand side by L, but in the left-hand side, we put order log n in place of L. So, and roughly speaking, least decodable code exists for a small L. Now we are interested in the case where the number of errors is close to n over 2. And you see that for such large for such a large E, the volume of the ball is already close to 2 to the n. So 2 to the k for Hadamard code is close to 1. So for Hadamard code, we can hope to decode up to close to n over 2 errors, but certainly not much, because already for n over 2, when E is n over 2, this inequality already becomes an equality, and otherwise it is just wrong. So the maximal number of errors the Hadamard code can correct is close to 1 n over 2, and it is possible to correct from the number of errors close to that. The theorem states that Hadamard code is n times 1 minus epsilon over 2. So we 2 times n least decodable. Sorry, not 2 to the n. Here we can even take the constant time, constant size list. 1 over epsilon squared least decodable. And the proof is the following one. So this means that if we take any Hamming ball of whose radius E is n times 1 minus epsilon over 2. So in this theorem, epsilon is any positive number. And we think of epsilon as some constant. For example, if epsilon is 1%, so we consider the number of errors, which is larger than 49%. So consider such a ball. We need to show that the number of coordinates in that ball is at most epsilon squared. So call the center of the ball by Z, and the coordinates in that ball by x1, x2, say xn. So we need to show that n is at most 1 over epsilon squared. And why is this? Consider, so assume again that our alphabet is not 0, 1, but minus 1, 1. So all the code words and also Z are sequence of minus 1 and 1. And we will consider inner product of sequences of n letters of this alphabet, considering minus 1 and 1 as normal real numbers. So assume, sorry, and we will use the following fact, that the distance, we know that the distance between any two the distance between two between two different code words of Adamar code is either n or n over 2. So let's divide them into groups. The code words which corresponds to a fine function where f0 is 0, and the second group where when f0 the constant term is 1. So, and in both groups, all the code words are pairwise or orthogonal, because if we take some code word X and some code word Y, both live in the first group, then their inner product is the sum of the products of plus and minus ones, and there are exactly half of plus ones and half of minus one in that sum, because the Hamming distance is exactly 1/2. So the inner product is 0. The same happens for code words in the second group. And now we will use the Parseval inequality. So call the first group, say A, and the second group B. And Parseval inequality states that the scalar product of any vector is at most the sum of its scalar product with vectors of some basis, assuming that all vectors in the basis are pairwise orthogonal. Actually, it's not important that they form a basis. It's enough that they are pairwise orthogonal. And we have seen that actually that this is indeed true for both groups. So, and here we need to put square, I'm sorry. This is sort of a projection of Z on X, and this is the length of Z. And in our case, the length of any vectors from plus minus 1 is n. And if we consider all the x's in the sum which are inside the Hamming ball, of course we obtain not more. So here we can say that we can restrict the sum for x's in the A such that the Hamming distance between X and Z is at most n times 1 minus epsilon over 2. And for such xz, this inner product is at least epsilon. And why is this? Z x is the sum of plus minus ones. And the number of ones is the number of positions where Z and X coincide. And the number of minus 1 is the number of positions where they are different. And we know that the number of positions where they are different is at least the number of positions where are different is not large, and there are some positions where the coincide is large. More specifically, the number of plus ones is at least sorry, we need the lower bound. So the number of ones is at least n times 1 plus epsilon over 2, and the number of minus 1 is at most this much, n 1 minus epsilon over 2. So in total we obtain epsilon because n over 2 cancels, and we obtain epsilon over 2 plus epsilon over 2 times n. So for each for each x inside the Hamming ball, we have that the scalar product, the inner product is at least epsilon. So we obtain that this sum is at least n, the number of such code words. Sorry, here we have not n, but inside this ball, divide our x's in two groups, A and B, and let n denote the number in the first group and m the number in the second group. And we will show actually that both n and m are at most n 1 over epsilon squared. And this is because this is at least n times epsilon squared, and hence times n, because this is, I'm sorry, this is n times epsilon. So somehow we obtain n in the left-hand side and n squared is the right-hand side, which is not proper. Сейчас, тут какая-то проблема. Сейчас, наверное, я это самое неравенство. Ну да. Для того, чтобы вот так записывать неравенство Парсеваля, нам нужно, чтобы эти самые иксы все были не просто попарно ортогональны, а чтобы у них норма была единица.
А может там скалярное произведение z на себя в квадрате должно быть, иначе как-то по размерности не очень. Слева.
Ну нет, ну теорема Пифагора, ну что говорит? Квадрат длины вектора равен сумме квадратов катетов. Нет, это вроде правильно. Тут неправильно вот что. Ну, неравенство Парсеваля — это аналог в сущности теоремы Пифагора.
Ну да, я поняла. Да, там просто иксы-то у нас нормированные.
Да, надо на самом деле, сейчас, надо их нормировать.
Да, нормировать надо, да.
Вот. Ну или скалярное произведение друг друга рассматривать. Ну давайте их нормируем. Значит, вообще иксы по длине у нас это самое, есть n, ну, квадрат длины есть n, значит, надо x на корень из n здесь брать, и тогда неравенство Парсеваля будет уже честно записано. Соответственно, здесь тоже будет корень из n. Здесь будет эпсилон квадрат разделить на n. Ну и тогда окей. And now we obtain at least n cancels. We obtain n times epsilon squared n, and so we obtain that n is at most 1 over epsilon squared. So, and the same applies for the number of code words from the second group. And so we obtain that in total we have 2 over epsilon squared. Sorry, this was my mistake. So the size of the list will be 2 over epsilon squared. And the whole list may be found by brute force search just in time polynomial in n, because for Hadamard code we have at most n equal to 2 to the m code words, and we just can look for all of them and find out which are in the ball. So, so more roughly speaking, Hadamard code can be decoded, at least decoded from errors, where the number of errors is close to maximal possible, n over 1/2. And this algorithm can be used in practice for a very small m, of course, because otherwise 2 to the m becomes very large. However, there is a more smart algorithm. And now I will present it. It's called Goldreich-Levin theorem. And Goldreich-Levin theorem assumes, in the Goldreich-Levin theorem, we assume that m is large, so, and n is very large then, so we can't afford brute force search, but still we want to do list decode Hadamard code in time. So we want list decode in time, which is polynomial, not in the n, but in m. So we are given a corrupted table of a function f, which has the length 2 to the m, which is exponential m, and we want to decode, we want to find a small list of candidates for f. So of course in polynomial time we can't read the whole table, but we will assume that we are allowed to read it in whatever place we want, and we actually will read the table only in polynomial number of places, and our algorithm will be randomized. We have designed such an algorithm for normal decoding, where we want to find f exactly. And that algorithm works in polynomial time, and it recovers f exactly, assuming that the number of errors is less than 1/4. But now we want design a similar algorithm when the number of errors can be larger than 1/4. The number of errors can be close to 1/2 of the whole length of the table. And of course, this is impossible. It's impossible to do that if we want to recover f, the function, exactly. But now we are allowed to output a small list. So here we will assume that this f is a known function. To recover recovered by a list of candidates, and we have, so to say, corrupted function. So unknown function, the unknown function is a linear function, a affine function. Corrupted f is not an affine function at all, it's just a sum function. So both function map f2 to the m to f2. And we are given g. We have g as some external procedure. That means that we are able to find g's value at any point. And the theorem states that there is a randomized algorithm that given, so the algorithm receives as input g, that corrupted function, epsilon. Epsilon is the number 1 minus epsilon over 2 is the number of errors. Delta is the probability of error, the algorithm allows to have outputs a list of size order m over epsilon squared delta squared in time, which is polynomial also in those parameters, m 1 over epsilon 1 over delta, that contains coefficients of f, unknown f. And here we assume that the Hamming distance between tables of f and g, the Hamming distance between tables of f and table of g is at most 1 minus epsilon over 2 times the total length of the table. So whatever g with that property the algorithm receives as his first input, the guarantee is that the list will contain coefficients of f, and I forgot to say with probability at least 1 minus delta. So the algorithm might err. That means that it might happen that the algorithm, the output doesn't include f, but the probability of error is at most delta, which can be taken arbitrary. So the only requirement is that delta positive and epsilon is positive. So whatever g and f with that inequality the algorithm receives, the probability of error is at most delta. So, and this is a very smart algorithm and also a complicated one. So you will need to make some efforts to understand the proof of this theorem. So the idea is the following one. If we, first of all, the coefficients of f, which we need to recover, can be found from its values, and be found from its values in m plus 1 linearly independent points. For example, from its value in all zero vector and its value in basis vectors like 0, 1, 1, 0, 0, 0, 1, 0, 0, and so on. So we just need to find with probability of error at most delta all these values. And to find the value in certain point x, so assume that x is one of these values. No, call this set, say m. 0, 0, 0, and so on. Actually, we won't use the fact that x has a special form. The value of f in any point can be found by the following procedure. So we know that if we shift x by any vector, and then subtract from it f. Actually, we need to take here the linear part of f without the constant term. So the linear part of f is the function f1 x1 plus f mxm. Then because of linearity, we will obtain just f of x. And this happens for all r, for all r. Okay, now instead, now of course we can use this inequality, because we do not know f, we do not know f bar, but let's substitute here f by g. Then this inequality will be true for a little bit larger than 1/2 of r's, because we know that the table of G is different from the table of F in at most, in a fraction of at most 1 minus epsilon over 2 positions. And so for all those positions where they differ, we will make an error, but for the remaining r's, we won't have any errors. And the point is that for whatever x we have fixed, if r is chosen with uniform distribution, then x plus r has also the uniform distribution. So we can say that this happens with probability at least 1 plus epsilon over 2 when r is chosen at random. And this allows, using the law of large number in the form of Chebyshev inequality, to find f of x by majority vote. So f of x is equal to the majority of f of x plus ri minus tilde f, g of x plus ri minus f of ri, where all r's are chosen, assume that there are capital N of them, are random. So what is majority vote? We know that this equality holds for a little bit more than 1/2 of randomly r's. That means that if we choose, say, capital N of r's, then with high probability, among them, the fraction of r's for which this inequality is true is close to the probability of these events, which is at least 1 plus epsilon over 2. So if the majority vote, then with high probability will output incorrect answer. So more precisely, this is true when R1, Rn are chosen. So the majority, the majority is over I, which ranges from 1 to n. And R1, Rn are chosen independently with uniform distribution. And this happens with probability at least 1 minus 1 over epsilon over 2 squared times n. And this follows from Chebyshev's inequality. Let's see why. because we will need the proof actually of that inequality. So first of all, let's introduce the variable xi here, which is 1 if this happens, if f of x indeed equals g of x plus ri minus tilde f of ri and 0 otherwise. Then for this, then we will consider the sum of this variable, and we know that the probability that each variable is 1 is 1 minus 1 plus epsilon is at least 1 plus epsilon over 2, which means that the mathematical expectation is at least that much. And now the Chebyshev inequality states that the probability that x1 plus xn differs from its expectation by at least, say, gamma, is at most the covariance of this variable over this gamma squared. And the covariance in our case first of all, because they are independent, the covariance is the sum of covariances. And because our variables take only value 0, 1, this is of course at most n, at most the number of variables. So we obtain at most n over gamma squared. Now recall that we consider the indicators of the right answer, and the algorithm will, a majority vote, will make a mistake if gamma is equal to epsilon over 2. So the algorithm makes a mistake if the majority says wrong. That means that xi I is 0 and not 1. But the expectation is at least 1 plus epsilon over squared. So for gamma equal to epsilon over 2 times n, this event is exactly means that we have made an error. And so the probability of, for that gamma, the probability of error is at most, gamma is epsilon over 2 times capital N, of course. So we need to plug here gamma equal to epsilon over 2n, and we obtain for such gamma n in the numerator and squared in the denominator, and so we obtain this bound. So the probability of error will be 1 over epsilon over 2 squared times n. And actually, the only place where we need that they are independent is this one. And what's important for the sequel, that this equality holds needs only that they are pairwise independent, because how this is proved? So their covariance of the sum, the covariance of any variable is equal to the expectation of its square minus the square of its expectation. In this case, this will be the expectation of the sum squared minus n, the expectation of xi, minus the sum of expectations squared. Now we will use the we will use the distributability laws, and here we obtain the expectation of the sum, which is plus 2 times xi times xj. This is the first term. And now we can use that expectation is a linear function. So we obtain expectation of xi1 squared plus expectation of xn squared. And it's enough that they are linearly independent to deduce that here we obtain plus 2 times the sum of expectation of xi, expectation of xj. So we do not need they are independent as a whole set of n variables. It's enough to use pairwise independence. And so we obtain from this so let's see what we had. So this will be equal the sum of expectation of squared plus 2 times the sum of expectations of pairs, products of expectations. And when we cancel everything which cancels, we will obtain the sum of covariances of our variables. So the point is that in the Chebyshev inequality, it's enough that they are linear pairwise independent, and we will use this feature of Chebyshev inequalities. So let's go back to our algorithm. So to recover the value of f in a certain point, we will make the majority vote where we need to choose the number n large enough so that the probability of error is close to 0. More specifically, we will choose n so that the probability of error, which is 1 over epsilon over 2 squared n, is less than delta over m plus 1. And that is because we need to recover f's value not in 1 point, but in m plus 1 points. So for each point, we can tolerate the error, probability of error, which is delta over m plus 1, so that the cumulative probability of error become delta. So we will choose n so that this inequality be true. And now let's go back to our algorithm. Now we have understood how many R's we need, but still we have a very difficult problem. To perform as the majority vote, we need to know bar F, so linear part of F. But this is unknown to us. We know G, but do not know bar F. And if we knew bar F, we could recover F exactly by this algorithm with a small probability of error. So now we will sort of trade off the knowledge of tilde F for the size of the list. We will increase the size of the list from 1 to some small number, and this will be the cost of becoming some knowledge of tilde F. More specifically, we will use a very special procedure to choose our R1 Rn. So procedure to choose R1 R capital N. So the procedure is the following. We pick at random some k, we will specify k later, vectors of dimension m. And we will set R1 Rn, where n will be 2 to the k minus 1. So actually, we can use k. Actually, we will use first k, then set n equal to 2 to the k minus 1, and k will be chosen that this number is large enough. So R1 Rn will be equal to the following set of vectors: U1, U2. It doesn't matter in which order they are arranged. I mean R's, the R vectors. So first of all, we put in our set of R's all these U's. Secondly, we put there all the sums. Then we put all the sums of triples. And so on. And the last vector we put is the sum of all of them. So in total, we obtain all possible non-trivial sums, and the total number of sums is 2 to the k, but we exclude the trivial sum, which is 0. And so we obtain 2 to the k minus 1. And the point is that those R's are pairwise independent, and each of them is uniformly distributed, has uniform distribution. So why are they linearly independent? Well, for example, consider U2 and U1 plus U2. Whatever U2 we fix, U1 plus U2 will be uniformly distributed because of U1. And the same holds for any two vectors in this list, because there is at least one U which is in one sum, present in one sum, and absent in another one. If we fix all values except for that, then the second will be fixed, but the first will be uniformly distributed. So that means that for any R's, or for any Ry, Rj, if we fix the value of Rj, still Ri is uniformly distributed. And also each of them is uniformly distributed, which is trivial because all UIs are uniformly distributed. So I assume here that all UIs are chosen with uniform distribution independently. Так, я сейчас хочу перерыв сделать. Скажите, все понятно в доказательстве леммы?
Да.
Так, давайте перерыв на 5 минут до 2 часов. Так, ну давайте продолжать. Окей. Now, why? First of all, let's use some notation. Let's denote this, say, by R of use. This set. So now I will explain why we will use such a such a procedure to choose R's. The point is that we still have the problem that we need somehow to find the capital, the bar F of Ri. But the point is that now this can be found from the following value, bar F of U1, bar F of UK. And this is because tilde F is a linear function, and each Ri is a sum of certain U's, and we can just compute this bit as the sum of corresponding bits from these bits. And this is a k-bit vector. So to make the majority vote, we just need k bits where k is small enough. Recall that 2 to the k minus 1 is our n, and the only requirement we need that n is at least 1 over epsilon over 2 squared times delta times m plus 1 actually. So we need to, we can choose 2 to the k just equal, choose the parameter k so that 2 to the k is equal to this guy, m plus 1 over delta times epsilon over 2 squared plus 1. And it might happen that this is not power of 2, but just take the closest power of 2. It's not important. We will, then 2 to the k will be at most 2 times larger than this value, but this is not important at all. The point is that 2 to the k is polynomial in our parameters, m, delta, and m, 1 over delta, and 1 over epsilon. And k is then logarithmic, so k is actually very small. To compute, to find the unknown information, we need logarithmic time number of bits. In other words, we can use the all possible values of this, all possible 2 to the k values of this vector. And for each vector, we can make the majority vote and then form a list for each value of unknown value of bar F in the points U1, UK. We will produce one entry of our list, and the list will have this number of entries, actually 2 times more, because this is not a power of 2, but this still a order of m over delta epsilon, actual delta squared, I'm sorry, delta squared epsilon squared. So this is our algorithm to produce the list, the algorithm which we prove to exist. So first we choose, we set k as was specified, and then we start with choosing u1, uk at random. Or better say F2. At random. Then, for each, call it alpha, alpha1, alpha k in F2. This is our, so to say, our guess for the values of unknown function bar f in those points. We do the following. For each x in our set of x's, so we need to recover the values of our function, say the point 0, 0, 0, 1, 0, 0, 0, and so on, in total m plus 1 points here. We do the following. Compute say call it beta e, beta of x, which is equal the majority vote of f of x plus ri. Sorry. First of all, we set here the second one, set r1, rn, where n is 2 to the k minus 1, equal to that we call it r of u1, uk. So the set of all non-trivial sums of u's. Now we have chosen our voters and take the majority vote here as was said, but here we use alpha 1, alpha k to compute this. So this is unknown to us. I'm sorry, here we use g instead of unknown, the known g instead of unknown f, and here we use alpha 1, alpha k to compute f tilde bar f of ri using the fact that ri is a linear combination of those values, and thus it's possible to use to compute f tilde f of ri, assuming that these are correct values. Otherwise, we obtain here some value without any meaningless value. A meaningless value. Anyway, once we have computed b of x, we compute coefficients of f from these values. From f of x for x, call this set, say, m for x from m. Of course, it might happen that sum of f of x here call it from beta of x. Call it f. So it's otherwise we have too many notations. From these values, it might happen so that some of them are incorrect. If at least one of them is wrong, we will obtain a wrong answer. And finally, once we have computed, include those coefficients in the list. Include them in the output list. And so, and this is the end of this 4. And you see that our list, and here is the end of it 4. So in this cycle, in this loop, we compute one entry on the list, and the total number of entries will be equal to 2 to the k, which is polynomial in M, 1 over delta, 1 over epsilon. And why this algorithm is correct? We need to show that with probability, the probability of error, and error means that our list doesn't include the coefficients of a genuine function f. Is it most delta? What do we know? That when we choose this at random, then with the probability of error, with probability list 1 minus delta, if we use here correct values, then we will obtain indeed all the values correctly, and so we will include in the list the genuine f when alpha 1, alpha k are chosen correctly. So for at least 1 minus delta fraction of all use, when we come in this loop for correct values of alpha 1, alpha k, we will include the correct f, coefficients of the correct f in our list. And so the theorem is proved. I mean, the correctness of our algorithm is proved. Вот вроде я закончил доказательство этой сложной теоремы. Спросите что-нибудь, если можно как-то помочь вам ее понять еще. Видно, что все так обескуражены, что даже вопрос невозможно задать.
Да, в точности.
Да, так бывает. Ай, ну, у меня то же самое было, когда я в первый раз слушал доказательства. Это, наверное, уже 10-й раз, так что не просто рассказывать, а понимать намного сложнее. Ладно, так или иначе, будем считать, что мы это проехали. Ну, по крайней мере, формулировка-то теоремы понятна была?
Формулировка-то, да.
Ну, ладно. Будем считать, что, по крайней мере, формулировку вы узнали. Ну, а доказательства ничего не поделаешь. Хорошо. Сколько у нас? Ну, у нас еще 20 минут, можно двинуться дальше. Ну, дальше будет проще. Johnson bound. Johnson bound, so to say, generalizes this observation that for which observation? The observation is the following one. We have a particular code, Hadamard code, whose relative distance is 1/2. And for that code, it's possible to decode from approximately 1/2 fraction of errors, more precisely 1 minus epsilon over 2 fraction of errors, with a small list. It turns out that with a little bit worse parameters, this is possible for any code whose relative distance is close to 1/2. More precisely, every nk1 minus epsilon over 2 n 2 code is 1 minus square root of epsilon over 2n 2n least decodable. So notice that the square root of epsilon is larger than epsilon because epsilon is less than 1. And so this number of errors is a little bit larger than this one, less than this one. So we can decode by a small list from a little bit less errors than the distance. And this is amazing because for normal decoding from errors without a list, just exact, we can decode from 1/2 of the distance errors, but here almost from that, from the number of errors equal to the distance, assuming that epsilon is small. So this is a statement of the theorem. Now I will prove it. We know that least decodability actually means that every Hamming ball with some center z of radius, which is in our case is 1 minus square root of epsilon over 2n, has at most 2n code words. So assume that these are code words in the ball. And we need to upper bound. We have to show that n is at most 2 times n. And we will use here the geometrical fact, which was used for the second Plotkin bound, that if we have in n-dimensional space certain number, capital N of vectors, non-zero vectors, which form pairwise obtuse angles, then the number of such vectors is at most 2 times the dimension, 2 times n. And these vectors will be xi minus square root of epsilon z. And again, we will assume that all our vectors live in minus 1 plus 1 to the n, where minus 1 plus 1 will be considered as real numbers. So In other words, we will use plus minus 1 as symbols of our alphabet. And so we will have here, this will be real valued vectors living in R to the n already, not just plus minus 1. And they will be non-zero, of course, because here we have plus minus 1, we subtract something which is less than 1 from them, so we can't obtain 0. And we need to compute pairwise inner products and to show that they are non-positive. So let's compute them. Xi minus square root of z multiplied by xj minus square root of epsilon times z. Using distributivity, or in other words, using the linearity of inner product, we can rewrite this as xi xj minus xi xj, xi z square root of epsilon, xi z minus square root of epsilon z xi xj, and plus epsilon the square of z. Now this is known what it means, because z is the vector of plus minus 1s. Its inner square is equal to n. So this is epsilon n. So we need to upper bound this, to bound this from above. Xi xj may be bounded from above using the fact that the distance of our code is at least 1 minus epsilon over n, which means that there are many positions where xi and xj are different, and each such position contributes minus 1 in this sum. So, in other words, xi xj is at most 1 plus epsilon over 2 times n, the number of ones, minus 1 minus epsilon over 2 times n, the number of minus 1, which is equal to epsilon n. Now, the second and the third terms may be upper bounded using that xi lies inside the Hamming ball of that radius. So this means that xi z is at least the number of coincidences, which is 1 minus square root of epsilon times n, minus the number of differences, which is at most 1 minus square root of 2 over n, which is square root of epsilon times n. The same applies for z xj, also at least n times square root of epsilon. And finally, zz is n. So we obtain that xi minus square root of epsilon z times xj minus square root of epsilon z is at most epsilon n minus, recall that we have the multiplier, the factor square root of epsilon in front of this inner product. So we obtain minus square root of epsilon times square epsilon n minus another square root of epsilon times square root of epsilon n and plus epsilon n. And of course, everything cancels here and we obtain 0. So the inner product between any pair of different fractures from this set is non-positive. So that means that they form obtuse angles. And by the geometrical lemma proven earlier, by a lemma proven earlier, we have that n is at most 2 times the dimension. So the theorem is proven. Есть вопросы? Мне кажется, уже простая вещь.
Ну да, нет вопросов.
Okay, good. And from this Johnson bound, we can derive the best known bound for binary alphabet, the best necessary condition, which is called Elias-Basaliga bound. I mean, it's very easy thing. I mean, an easy corollary from Johnson bound. If n k 1 minus epsilon over 2 n 2 coexists, then we have the volume of the ball of radius 1 minus square root of 2 n times 2 to the k is at most 2n 2 to the n. And this is because the following thing. Assume that such code exists. Then by Johnson bound, that code is, so call it C. By Johnson bound, bound C is 1 minus square root over 2 times n, 2n least decodable. And for least decoding, we know that if something is least decodable, there is a necessary condition, which is an analog of volume bound. If a code is least decodable from this much error, then the volume of the ball of that radius times 2 to the number times the number of coordinates is at most 2 to the n times the size of the list, which is 2 to the 2 times n in our case. So we use first Johnson bound, then we use the analog of the volume bound, or volume bound for least decoding. So it's a very simple corollary of the Johnson bound. And the point is that this Elias-Basaliga bound improves the best known bound so far, which was the improved singleton bound. So let me write a graph. So this is d over n, this is k over n. So this is 1, and this is 1/2. So this is the improved singleton bound. Oh, let's use this. Sorry. So this is the singleton bound. And now our bound is the following one. Let's use this. Something like that. It's convex. So this is the bound V of 1 minus square root of epsilon over 2 n times 2 to the k is at most 2 to the n, 2 to the n, assuming that this is d over n. So more specifically, we need somehow to find epsilon from d over n. This will be some quadratic expression, and then substitute here that quadratic expression. I'm sorry, d over n is 1 minus epsilon over 2. So first of all, we need to express epsilon through d over n as 2 times d over n 1 minus 2d over n. And then substitute this expression here in place of epsilon, and so we obtain this bound in terms of d over n. And so one can verify that indeed in the points in this point they coincide. So these points, this for epsilon, which is 2, which is 0, we obtain this point. So if epsilon is 0, then this is 1/2. So the volume of the ball is about 2 to the n, and so we obtain k over n equals 0. If epsilon is 1, then d over n is 0, and this will become also 0. So this is negligible, and we will obtain just that k is at most n. So k over n is at most 1. But when epsilon is between 0 and 1, we obtain a better bound than the improved singleton bound, and also the better bound than the volume bound. The volume bound will look something like that, also above this. So this Elias-Basaliga is the best bound for binary code, the best necessary condition. Вот, ну хорошо, я как раз уложился. Спасибо. Значит, следующая лекция у нас завтра. Не забудьте, в обычное время по старой ссылке заходите.
Извините, а можно вопрос?
Да.
А если не удастся набрать вот 65% баллов, будет зачет в обычной форме?
Нет, никакого зачета не предвидится. Постарайтесь набрать 65 баллов. Зачет
можно будет какую-нибудь задачку дополнительную получить, например, если будет
ну смотрите, это я иногда делаю индивидуально. Но если человек набрал там, я не знаю, 63%, я ему разрешаю. Но я никаких обещаний сейчас давать не хочу.
Понял вас.
Вот
понял.
так. Ага.
Все,
ну ладно, все, до свидания.
До свидания.
До свидания.
До свидания.